Yep.
Are you ready?
Yep.
Okay, thanks for coming. So this week we have Tung Nguyen from Oxford. He's my academic brother. And we talk about high-boundedness.
Yeah, so thank you for coming. Thanks you for the invitation. It's actually great to be back here. I think this one is my second time talking at the IBS Discrete Math Seminar. And the first time was 6 years ago, actually, when I was still an undergrad at KAIST. And then it's been 6 years, and back then Sang-Yu was my academic advisor for a bachelor's degree, and now I mean, we are academic brothers. Yeah, so in a short period of time. And so, right, so I would like to talk a bit about a recent result that just came out a couple of months ago. The result is actually the title of the talk. And before going to the talk, I would like to acknowledge my current two affiliations at Oxford. The first one is the Mathematical Institute, and the second one is my college, Christchurch. They have been very supportive and immensely helpful during the first couple of months of my life in the UK. So I just want to acknowledge them here. Okay, so now let me go into mathematics. And in this talk, I will talk about finite graphs. All graphs in this talk are going to be finite. And I'll be mostly focusing on two parameters. One is chromatic number, chi, and the other is the clique number, omega. So these two are very familiar, and I guess all of you already know about these two. And of course, from the theory side, we always know that chi is at least omega. So in having a big complete subgraph is, of course, the most obvious reason why a graph can have large chromatic number, right? And so it is kind of natural to ask the reverse question. So if I give you a graph with large chromatic number, then can you always guarantee me a large clique? Of course, this question was already investigated many, many years ago. I guess even before all of us were born. And the answer is no, of course. There are lots and lots of classical constructions of triangle-free graphs with arbitrarily large chromatic numbers, right? So these examples were all from the 40s and the 50s of the last century, right? Okay, so one of the main themes of graph theory during the past couple of decades, has been trying to understand local properties of these graphs. So what can be said about the local structures of graphs with large chromatic number and with bounded clique number? What is going to happen if the chromatic number is a lot bigger than the clique number? All right. And in this talk, I'll be focusing on the relation induced subgraphs. So in graph theory, local properties can usually be stated in terms of induced subgraphs. And here for two graphs, H and G, I'll say that H is an induced subgraph of G if H can be obtained from G just by removing vertices. So the rule here is that you have to maintain the pattern of the edges and the non-edges among the remaining vertices. Okay. And whenever I talk about a class of graphs, I'll be talking about an infinite set of graphs that is closed under taking induced subgraphs. Okay. And for any graph H, I'll say that a graph G is H-free if it has no induced subgraph containing H. No induced subgraph isomorphic to H. Okay. So please interrupt if you have any questions. Okay. Right. So the study of graphs with chromatic number a lot bigger than clique number was put forth formally by Gyárfás 40 years ago. And that's through the notion of chi-boundedness. So here in this talk, I'll say that a graph class is chi-bounded if there's a function f such that the chromatic number of every graph G in the class is bounded by f of omega G for every graph G in the class. And in this case, I'll say that f is a chi-binding function for this class. Okay, so a class can have a lot of chi-binding functions. And the inspiration of Gyárfás for this definition also came from the notion of perfect graphs, which is a very well-known one. So we know that a graph is perfect if and only if number is equal to chromatic number for all of its induced subgraphs. So in other words, the class of perfect graphs is exactly the class of graphs for which you can have the identity chi-binding function. Okay. Right. Speaking about perfect graphs and induced graphs, of course, the most famous one is the strong perfect graph theorem of Marjanovsky, Neil Robertson, Paul Seymour, and Robin Thomas from 25 years ago. And what it says is a graph is perfect if and only if it contains no cycle and anti-cycle of length at least 5 as an induced graph. In this language, you say a graph is perfect if and only if it has no odd hole and no odd anti-hole. Okay. And so this gives a very nice if and only if characterization of perfect graphs in terms of forbidden induced graphs. Okay. Right, so this was one of the highlights of mathematics 25 years ago. But still, in high-boundedness, there are many fascinating open questions. And perhaps the most important one is the Gyárfás-Sumner conjecture, which was independently posed by Gyárfás and by Sumner maybe 40, 50 years ago. And what this asserts is that for every tree T, the class of T3 graphs is chi-bounded. So what this says is as long as you forbid an induced tree, then the chromatic number is going to be bounded by some function of the clique number. And here the function depends only on the choice of the forbidden tree T. Okay. Right, so this is a very beautiful conjecture and a very nice example of local-global interaction in graph theory. And this remains wide open despite a lot of work during the past 50 years. And the nice thing about this is that if you try to relax the condition G in this conjecture, if you allow the forbidden graph T to contain a cycle, then it's going to be false. And this is because of the probabilistic construction of Erdős, again, from many years ago on graphs with large girths and large chromatic number. And here large girths means no short cycle. Okay. And the intuition behind this construction is that you can actually have graphs with arbitrarily large chromatic number and locally tree-like, in the sense that if you pick any vertex and then you try to zoom in a border product radius around that vertex, then what you're going to see is just an induced tree. And here, the Gyárfás-Sumner conjecture predicts the other direction. That is, perhaps small induced trees must appear everywhere. All kinds of small induced trees must be everywhere in this kinds of graphs. Okay. Right, and so here's a list of known cases. I mean, probably not all of them, but most of them. So some known cases of Gyárfás-Sumner. So basically, this is still very much open, but over the years, there has been quite a bit of work on special cases of this. The first two cases were stars and paths, which were all done by Gyárfás when he first introduced the notion of high-boundedness. So for induced stars, it is not very hard to see. If you forbid a star as an induced subgraph and you have bounded clique number, then you're going to have bounded mass degree. And because you have bounded mass degree, you're going to have bounded chromatic number. And it is not hard to see that you can choose the chi-binding function to be a Ramsey function. Okay. And the case of path was done by what is known today as the Gyárfás path argument, which is also a very useful one for different reasons. And this argument gives you an exponential chi-binding function in terms of clique number. Okay. So 10 years after Gyárfás introduced the notion of chi-boundedness, Alex Scott, in his PhD thesis, proved this conjecture for subdivided stars. So what's happening here is that Alex actually proved this conjecture if you replace excluding one single induced tree as excluding all induced subdivisions of any given tree. And so this subdivided star follows as a result because for every subdivided star, all of its induced subgraphs contain it as induced subgraph. Sorry, all of its subdivisions contain it as induced subgraph. Okay. And around the same time, Kirset and Penrice verified this conjecture for trees of radius 2 using the method known as a template. And this was extended by Gyárfás and Zhu a few years later to a couple of trees of radius 3, which was extended further by Erdős and Polynomial maybe 20 years later to more types of trees of radius 3. But in general, this conjecture is still open for all trees of radius 3. And one of the main obstacles here is that as long as there are a couple of vertices of degree at least 3 very far away in the forbidden induced tree T, then that's going to be quite a bit of technical issues. Okay. Yeah, but anyway, this conjecture is still very much open. Right. So the reason why I didn't really tell you about the chi-binding functions coming from the last 3 cases in this list is just because they are all enormous, in the sense that they are multi-layers of exponentials, and in some sense they are very ineffective. So you can see we started out with a polynomial chi-binding function, and then we moved to an exponential one, and then the last 3 are layers of exponentials. So the feeling here is that okay, so these results might be good for verifying some sort of intuition for small cases of Gyárfás, but they might not be very satisfying because of these huge chi-binding function. And so over the years, people have wondered about, okay, so whether I can actually force all of these chi-binding functions to be polynomial. And the notion of polynomial chi-boundedness came out of this. So I say that a chi-bounded class is polynomially chi-bounded if it admits a polynomial chi-binding function. So you can actually make the chi-binding function to be a polynomial in the clique number. And of course, given Gyárfás, you can formulate the polynomial Gyárfás conjecture that says for every tree T, the class of T3 graphs is actually poly chi-bounded. Okay, so now let me try to make a little bit of remarks on these 2 conjectures. So I guess, at least from my experience, for many people in the area of chi-boundedness, Gyárfás is kind of believable. It is plausible. And the point here is that there is no requirement on the chi-binding function. If that is true, then maybe the first proof could use some sort of dynamical system or ergodic theory techniques, and it's not going to tell you what the chi-binding function is. It just shows that a chi-binding function exists, but there is no shape, and that's still fine. That's still going to be very, very interesting. But poly Gyárfás seems to be, maybe a little bit too much to ask for at the moment. There is a half structural, half extremal problem. Structural because we want to understand what's going to happen if you exclude a tree as an induced subgraph. But extremal because you want to optimize the chi-binding function if it exists. So, and right now we don't seem to have any tool or any good construction to prove or disprove this conjecture. Okay. So given that Gyárfás is still very much open, this is of course very much open as well. And again, we have no idea how to prove or disprove it in general. So what is known about this poly Gyárfás conjecture? Well, so the state of the art up to 5 years ago was that it is confirmed for double stars, which is this configuration. And this was done by Alex Scott, Paul Seymour, and Sophie Spiekel. And in the literature, double stars are also known as trees of diameter 3 or trees with no induced P5. So basically, poly Gyárfás was verified for all trees with no induced P5. And here P5 means the five-vertex path, okay, the path on 5 vertices. So, of course, given this result, it is kind of natural to ask the obvious question. So what about P5? Well, it turns out that you don't really need to know about this result in order to ask about P5, because this already appeared in the chi-boundedness problem list of Gyárfás from 40 years ago. So the story was Gyárfás managed to prove the exponential bound for P5, and then he asked the question, okay, so whether, for P5 free graphs, we can improve the chi-binding function significantly. And then he was asking to find the correct order of magnitude for the optimal chi-binding function for P5 free graphs, And recently, I tried to reach out to him to ask him so what he meant by order of magnitude. And then what he confirmed was he wanted to get a polynomial chi-binding function. So basically, this was already there. And not just Gyárfás, but Kestet and Penrice and Trotter around 1995. And they also made this question explicitly in one of their papers.
Maybe he changed his mind over 30 years.
Yeah, maybe.
Now he clarified, oh, maybe, yeah.
Yeah. Yeah. Right. So, so the polynomial chi-boundedness problem for P5 is a very specific problem, right? Just ask a P5, and this is a very simple question. You can actually condense, you can squeeze everything in just one sentence. And so it is not very surprising that over the years, there has been a lot of attempts to try to get a little bit on it. And it became one of the most well-known open problems in chi-boundedness. And there's a lot of papers trying to prove partial results and singling out this one as one question that must be addressed. So just to give an idea of how hard people in the area tried, here is a list of maybe 2 lists of partial results on this specific problem during the last 40 years. So basically, there were 2 lines of research. The first line was to obtain better and better chi-binding functions. So here in this part, I would say the chi-binding function is f, and we start from exponential f with Gyárfás, with incremental improvements until 2021, when Alex Scott, Posimo, and Sophie Spurkle managed to push exponential to quasi-polynomial. And then in my PhD thesis, I managed to push it down a little bit more. Yeah, but the shape was still basically quasi-polynomial. The second line of research tried to confirm polynomial chi-boundedness for classes of types P5 and H3. So in addition to P5, you want to exclude something else. In this case, that's H. And it seemed like the most popular one was when H has 5 vertices. And there are 2 cases which were probably the most well-known. The first one is when H is the house, which is the complement graph of P5. And this was done by Fouquet and Giacomakis and Mer and Thulier. And the second one was when H is the bool, which is this configuration. And that was done by Murray Chudnovsky and Sivaraman. And interestingly, the chi-binding function f resulting from these 2 cases were both of this type, x plus 1 choose 2. So basically quadratic. But still, with a lot of effort, it even remained open whether you can get polychi-boundedness when H is a 5 cycle. So as far as I know, this P5C5 subproblem was also a pretty well-known one, at least in the chi-boundedness community. Okay. Right, so now I will try to explain a bit why people in the area care so much about this problem. Even though it appeared to be a very specific and a very simple looking one. Okay, so the first reason is that over time, people came to realize that polychi-boundedness is a very delicate notion, and it indicates exceptionally good control over chromatic number. And to explain this, I would like to go back to the list of known cases for Gyárfás-Sumner. And as I said, most of them were done with very enormous chi-binding functions. And there are primarily 2 reasons for this. The first one is that you try to do induction on omega. So from omega, you want to push it down to omega minus 1. The second is that you want to apply Ramsey to clean structures. So, these 2 kinds of operations will pop up, will increase the chi-binding functions very quickly. And so that's why you see most of the cases were done with super exponential chi-binding functions. So people in the area have wondered, okay, so all of these cases are, seem to be, huge, right? The functions are huge, and they apply not just to special cases of Gyárfás-Sumner, but also to most of the known results in chi-boundedness. And whenever you have a result confirming that some class of graphs is chi-bounded, it is going to be with some enormous chi-binding function. So there was a meta question by Louis Espéry from more than 10 years ago asking, okay, so could it be true that chi-boundedness is actually polychi-boundedness? I mean, could it be true that these two notions coincide? I mean, of course, with all of our knowledge, our intuition on chromatic number being something very hard to control, this already looked like very too good to be true, I think. It's actually the impression of the area. And so it is not very surprising that there is a counterexample. But what is even more surprising is that actually polychi-boundedness is very far from chi-boundedness, because you can actually construct classes of graphs that are chi-bounded with arbitrary optimal chi-binding functions. So here, optimal means you start from the class, and for every k, you collect all graphs in the class of clique number, exactly k. And because the class is chi-bounded, the maximum chromatic number of all of these graphs is finite. And so you can define f of k to be that number. And that f is going to be the optimal chi-binding function of the class. And what was shown by Marcin Briansky, James Davies, and Bartosz Dworczak 4 years ago was that you can actually construct chi-bounded classes G with arbitrary optimal chi-binding functions f, satisfying some cubic condition like this. But anyway, what this shows here is that chi-boundedness and polychi-boundedness are actually very far away from each other. And let's imagine that, if you're trying to prove that a certain class of graphs is polychi-bounded, then no matter how close you are to polynomial chi-bounded, you are still infinitely far away. Right? So only until that you can get actual polychi-boundedness that you can declare victory. Okay. Yeah, and so this somehow elevated the status of the P5 problem a little bit more, because in terms of naturality, the P5 problem became the only one that was undecided. Okay. The smallest open case of poly-Gyárfás-Sumner, and also because the constructions coming from these counterexamples don't quite disprove polynomial Gyárfás-Sumner. Okay. Right. Yeah, and also it shows that perhaps many known chi-bounded classes are actually not polynomially chi-bounded, and the chi-binding functions, the huge chi-binding functions coming from the proofs, are kind of reasonable. In the sense that the corresponding optimal chi-binding functions have to be at least as large as that, or maybe or as close as large as that. Okay. Right. So the second one is going to be about the class of P5 free graphs, because this seems to be, this class seems to have some sort of special role in algorithmic and structural graph theory. And so we've been talking about trying to prove that you can control chromatic number exceptionally well for this class of P5 free graphs. And it might be helpful to view this problem from an algorithmic point of view for P5 free graphs in terms of coloring these graphs. And it turns out that we can view this class as a critical trackability boundary for coloring graphs with a forbidden induced path. So P4, P5, P6, P7, and so on. The point here is you might ask, okay, so why we care about P5? Why not P6, P7, or all the way to Pk, right? Why just P5? So here are a couple of results that were obtained by different groups of people throughout the years. Okay, so I will consider the problem, the decision problem of K coloring. Okay, where K is part of the input. So I have an input graph. I have an input number K, and then I want to decide whether my input graph has a proper coloring using at most K colors. Okay. So of course, for P4 free graphs, there is always in P, always polynomial. We know too well how P4 free graphs behave. They're just co-graphs. They're built by repeated complete joins and disjoint unions starting from copies of one-vertex graphs. And so you can actually compute the chromatic number of these graphs exactly in polynomial time. So it's not a big deal. Well, but if you jump from P4 to P5, then this returns to FP complete. And this was done 25 years ago by Dan Prowl and Patrusville and Tuza and Worlinger. Okay, so that's when k is part of the input. I mean, if the number is part of the input, then the problem returns NP complete for P5V graphs already. Right. But what if k is fixed? So let's say I have an input graph, and then you ask me whether I can color this thing for, I mean, with 1,000 colors, let's say. Then what's going to happen? Well, so here comes the transition point. For P5V, the problem returns to P. So on the same class P5V graphs, you ask for, I mean, coloring graphs. You ask to decide whether you can color this graph by using some number of colors. If the number of colors k is part of the input, then the problem is NP complete. But if k is fixed, then the problem is polynomial. Right? So what if I try to jump from P5 to P6? Then, well, already for 5 colors, the problem returns NP complete. So the message coming from these results is that, okay, so for P5V graphs, the original problem of polynomial chi-boundedness might be non-trivial, but at least might be still doable. So doable, but maybe non-trivial. And so that's why, I mean, this class of graphs, I mean, should be treated specially. And also the message here is that if you're trying to do polychi-boundedness for graphs with a forbidden induced path, if you're trying to prove polynomial Gyárfás for excluding PT in general, then before you want to get P6, P7 or anything, perhaps you should be able to do P5 first before going on. Okay. Right. And the structural reason for these graphs is that until now, I mean, despite the the simplicity, the seemingly simplicity, and also the a lot of work coming from people in structural graph theory, there is still no structural decomposition hint for these graphs. So basically, nothing much is known about these graphs in terms of decomposition. Okay, and this seems to be a very critical point for polychi-boundedness, because most results obtained, most positive results obtained in this direction have been done by some sort of structural decomposition. So for example, in the strong perfect graph theorem, if you exclude all odd cycles and odd anticycles of length at least 5, then you're perfect. Or for even whole-field graphs or circle graphs, one to clique width and then bounded twin width. All of these results were done by some sort of decomposition. And the idea here is that you start from a class of graphs that you want to show polychi-boundedness for. And you pick any graph, and what you would like to show here is that you can decompose the graph into graphs that belong to substantially more restricted subclasses. And now what is left to do is to do 2 tasks. The first one is to ensure that these subclasses are already polychi-bounded. And the second thing is that how you decompose the graph preserve polychi-boundedness. And all of and these 2 steps were basically done for all of these examples. Yeah, but because there's still no such hint for P5V graphs, this was also a source of motivation for the second line of research that I was talking about. That is to try to exclude something else. And the hope here is that by excluding something else, you can get some sort of decomposition, which might give some hint for the general class of P5V. Okay. Yeah, but after a lot of effort, there is still very much open. And it is not even, we're not even sure if such a decomposition result would exist. Okay. Yeah, so the third reason that I want to talk about is the Erdős barrier. So why would I say barrier? Because it is related to another well-known conjecture in graph theory, which is the Erdős conjecture. And what it says is a prediction for general classes of graphs with a forbidden induced subgraph. So formally, for any h, I can find some c positive depending on h only, such that if I have no induced copy of h, then I'm going to see a clique or a stable set of size at least n to the c. And here n is the number of vertices of the graph that I started with. Right, so this is basically diagonal Ramsey with structural constraints. And this is because, in general, if you remove this H precondition and you only ask for general graphs, then the best that you could hope for is just logarithmic. So basically, what Hajnal says here is that as long as you exclude any given graph as an induced subgraph, then you're going to see a big jump from logarithmic to polynomial. Okay, and this one is still very much open. Right, and even though this is still wide open, from the point of view of polynomial-boundedness, Hajnal is just a very small step. It is just a baby step, and here's why. So polynomial-boundedness implies Hajnal because, so I start from this property. I know that omega to the d is at least chi, and I can apply the trivial inequality chi is at least n over alpha, right? To deduce that alpha times omega to the d is at least n. And so I can deduce Hajnal, right? Okay. And one observation here is that if I look at the second inequality, the middle one here, then one thing here is that while Hajnal is predicted to be true for excluding any given graph H, if you demand for the second inequality, I mean the middle one, alpha times omega to the d is at least n, then the graph H that you're excluding must have no cycle. And the reason here is because actually of the construction of Erdős. So if you go back to his paper, or you can consult the Alan Spencer book, then what you get is actually for any g at least 3 and for sufficiently large n, you can actually take a sparse random graph, and then you get an n-vertex graph G with no cycle of length at most G, and with alpha roughly at most this number. So basically alpha is properly sublinear in terms of n. And if you plot these in the second inequality, then you will see that if H contains a cycle, then this cannot be true. Okay. So moving from Hajnal to this off-diagonal form already requires that you're really using the hypothesis that you're excluding a tree or a forest as an induced graph. Okay, and of course, going from this middle inequality to polynomial-boundedness is another story, because now you have to use chromatic number, which is again another mystery, right? So what's been happening for polynomial-boundedness so far for most results is that, so usually we know that the class of graphs satisfy Hajnal in a relatively simple way, and then with a lot of work, a lot of structural decomposition ideas, you can get polynomial-boundedness. So what has happened so far is the proof for polynomial-boundedness is usually a lot more complex than the corresponding proof for Hajnal. Okay, so going back to the case of P5, then perhaps so P5 is known to have to satisfy Hajnal, and perhaps it is the proof for P5 is actually the most complex one among all of the confirmed cases. So that's another point to show that maybe polynomial-boundedness for P5 graphs is not going to be very simple. Okay, so the main result that I want to talk about today is the confirmation of this conjecture. So basically, now it is known that the class of P5 graphs is polynomial-bounded. Okay, and just one remark about the result is that, in case you may wonder, and in case you might be interested in Hajnal, is that whether this is going to give a new proof of Hajnal, and the answer is no, because it uses Hajnal as an input. So, okay, so the proof uses Hajnal as a stepping stone, as a black box, to do some sort of argument, which I will tell you later. And this Hajnal result was recently done by Alex Scott and Posimo and myself recently. Okay, so without Hajnal, this polynomial-boundedness result cannot be done. Okay, cannot be proved. Right, so in the last maybe 20 minutes of a talk, we try to give a very high-level overview of the main ideas used in the proof. And it seems that, these ideas were not used before in chi-boundedness. So I will try to go very slowly. But the framework that I introduced here, to solve this problem is what I would like to call chromatic density. So what I would like to show here is that I view the chromatic number as some sort of measure, satisfying some axioms. And then I would like to see how the p-phi-free condition would influence the chromatic number of the induced subgraphs of the graph that I started with. Okay. So all of the proofs, all of the arguments are just going to be about how chromatic number behaves as some function or some measure satisfying a certain list of axioms. And the clique number is set aside. So much of the proof is not going to be about the clique number. It is going to be about chromatic number. Okay, so what are the axioms I talked about? Well, I haven't been able to find a better terminology. So let me say this is a measure. So any function mu from the subsets of Vg to the real, to the non-negative reals is called measure if first every vertex has mass exactly 1. Okay, has measure exactly 1. That is just a normalized condition. The second is that for any two vertex subsets A and B, the measure, the mass of A and the mass of B are going to be at most the mass of the union. So what this implies is that this measure function is increasing monotone. Okay, and we have equality case if A and B are disjoint and undercomplete to each other. Undercomplete here means that the graph G has no edge between these two subsets. Okay, and the third axiom says that again for the same A and B, the sum of the masses of A and B is going to be at least the mass of the union. Okay, and here equality holds if A and B are disjoint and you have a complete bipartite subgraph between these two in G. So the proof is just going to be about the chromatic number satisfying these three properties. So there's nothing about degeneracy, nothing about extracting complete bipartite graphs that you would usually see in chi-boundedness. And also no recoloring or no product coloring, nothing. Just about these three properties. And what is interesting here is that the clique number, the chromatic number, and fractional chromatic number are all measures on the same graph. They all satisfy these three properties. And you see, it is not very hard to show that for any measure mu, you know that mu is going to be at least omega and at most chi. So basically, chi is the strongest measure and omega is the weakest measure. So another way to interpret chi-boundedness here is that you're trying to polynomially bound the strongest measure by the weakest measure. So if the argument works for any measure, and then you can deduce the bound in terms of omega, then that automatically holds for chi, and vice versa. If you know that chi is at most some polyfunction of omega, then you know that any measure also satisfies this property. Okay. Right, so the first idea I would like to say is chromatic quasi-randomness. And the starting point of this is the following result of Erdős from, again, 40 years ago. And it is a general graph structure theorem for graphs with a forbidden induced graph. And what it formally says here is that for any given density parameter epsilon and any given graph H, I can get some delta such that if my graph has no H induced subgraph, then I can find a linear size induced subgraph with shrinkage factor delta such that this induced subgraph is very sparse or very dense with the density parameter epsilon. Okay? And this is one of the very nice examples of quasi-randomness in graph theory. And what this basically says here is that if the edge distribution of your host graph is not being very close to random, then you're going to contain induced copies of all small graphs. Okay. Yeah, and the proof of this, the first proof of this uses the regularity lemma, which is again another source of motivation for quasi-randomness. And here's a picture. So basically, we have two cases, sparse or dense. And over the years, this result of Erdős became very useful in recent progress on Erdős Hajnal. And here's why. Now, let's try to see. Because I'm talking about excluding P5, which is a tree, what's going to happen if I exclude some tree as an induced subgraph? Can I improve this result of Erdős? And the answer is yes, because in the sparse case, it was shown by Chudnovsky, Scott, Simmer, and Spurgo that actually for any tree T, I can find some epsilon depending on T only, such that if G is T3 and has at least two vertices and is sparse in this sense, then I can find two vertex subsets and they compete to each other and of linear size. Okay, and here linear is again in this sense. Each of them has at least epsilon times G vertices. So if I try to plug this trees and linear anti-compete pairs theorem into this result of Erdős, then what I'm going to have here is that, again, for any given density parameter epsilon, if I exclude tree, then I can get a linear size anti-compete pair or a dense induced subgraph, depending on the density parameter epsilon. Okay. So the first idea of the proof is to try to formulate a similar result of this type for P5 free graphs. And of course, hopefully, I'll be able to extend it to paths or to trees, but right now, I'll just limit it to P5. And it is going to be a similar form, but for chromatic number instead of these counting vertices. These counting vertices statements. So what do I want to do? So first of all, it is not very hard to come up with a similar form for chromatic number for the first statement, for the first outcome. You can say chromatic number of A and chromatic number of B are going to be at least delta times chromatic number of G. That is fine. But finding a suitable analog for the second outcome requires a bit more thought. And the notion that I would like to introduce here is the notion of epsilon chi dense graphs. So I say that a graph G is epsilon chi dense for any given density parameter epsilon if the chromatic number of the non-neighborhood of any vertex V in the graph is going to be less than epsilon times the chromatic number of the host graph. So this can be viewed as an analog of dense graphs with high mean degree in this sense. Okay, and this is because if you have a graph with mean degree at least 1 minus epsilon times the number of vertices, then you can just flip to the complement, and then you say, the complement has bounded mass degree, and which means that in the original graph, every vertex has very low number of non-neighbors. Another way to interpret this is that this can be seen as a replacement of cliques. And if you drop the neighborhood of any vertex in my graph, then the chromatic number is going to shrink significantly. Okay. So let me just make a remark that the notion of epsilon chi dense graphs and this traditional notion of high mean degree can be very different in general. And to say this, so first of all, I can take a complete multipartite graph, and then I make the parts very unbalanced in terms of size. This is going to be epsilon chi dense, of course, but it is not going to be dense in the traditional sense because the parts are unbalanced. So to see the other way around, I would like to start with a complete multipartite graph where every part has the same size. And then after that, I'm going to put a sparse random graph into each of these parts, of different levels of sparsity, so that the chromatic number is going to vary significantly. And so the resulting final graph is going to be dense in the traditional sense, but not going to be epsilon chi dense. You can check it. Okay. So these two notions can be very different. And so what this means here is that if you want to work with this notion of epsilon chi dense, then this seems to require some sort of new argument. And the result that I would like to communicate in the first step is an analog of the previous one for P5 graphs. So in any P5 graphs, I can find an incomplete pair with linear chromatic number, or an epsilon chi dense induced graph with linear chromatic number. And here linear depends on the density parameter epsilon that I started with. Okay. Right, so you can interpret this as some sort of chromatic quasi-randomness result. That is, if the chromatic distribution of your host graph is not very much disrupted, right? I mean, it's not very much disrupted, then you are going to contain a copy of P5. So hopefully this can be extended to more configurations. The reason that I said this is because the proof uses the Gyárfás pass argument, which is a very well-known tool in time-boundedness. And the result here is by Gyárfás, and what it showed was if you have no induced P5, then you're going to contain a vertex such that the chromatic number of its neighborhood is going to be at least 1/3 of the chromatic number of the whole graph. And this linear factor, 1/3 mean could be 1/4 or 1/10. It doesn't matter. But I mean, I only need it to be a linear factor. So this linear factor is the very reason why I could produce such a chromatic quasi-randomness lemma. Okay. So because the Gyárfás pass argument works for PK in general, so maybe it can be extended to PK, but so far I have not been able to do it. Okay. Right. So that is the first idea. The second idea is about controlling these, anti-compete pairs, high chromatic anti-compete pair. Okay, so again, from the previous quasi-randomness result, we know that if P has no induced P5, then either we can have a linear chi anti-compete pair or a linearly chromatic dense induced subgraph. And because I said that the second outcome is a bit closer to being a large clique, then it seems like the second outcome is going to be useful in some sense. But if you know about chromatic number, then you will see that, well, the first outcome seems very, very natural, but useless. The reason here is just because chromatic number is, remains the same under disjoint union, right? So basically, you cannot infer anything from the axioms of chromatic number, besides the fact that now you have two sets, incomplete and a large chromatic number. So the second idea is to try to build on these incomplete pairs to decompose the graph globally into some sort of structure that is going to be useful for our purpose. So here I don't try to decompose P5 graphs into more manageable pieces like what happened in polynomial so far. What I would like to do is to decompose these graphs along linear chi incomplete pairs so that I can finally focus the problem into just one case of chi-dense induced subgraphs. Okay, essentially one case. Yep. And so why is this useful for P5 graphs? And this is because of this very simple assumption. So first of all, again, I would like to assume that because I don't care much about linear factor, I can assume that every induced subgraph of G with linear chromatic number is going to contain a linear chi incomplete pair. Otherwise, I'm going to contain a linear chromatic dense induced subgraphs, and I win. Okay, so under this assumption, what I want to use is going to be this observation about P5 graphs. So first, I start from two vertex subsets incomplete to each other, A and B, right? And here I'm assuming that they have high chromatic number with respect to G. And because I'm doing chromatic number, I can assume that these two vertex subsets are connected. Okay. Of course, I keep conflating vertex subsets with induced subgraphs, but I hope that's fine, right? And also at the same time, I can also assume that the host graph G is connected as well, because I'm doing chromatic number, right? So the observation here is that in my graph G, if I see another vertex V outside of these two A and B that has a neighbor and a non-neighbor in both A and B, then I can build a P5. And it's kind of simple, right? So V has a neighbor and a non-neighbor in A, and A is connected. So A is going to contain an edge such that one endpoint is adjacent to V and the other endpoint is not. And the same for B. And from these 5 vertices, I can build a P5. Okay. So this one is a very simple but very powerful observation about P5 free graphs. Right, and because I assume the graph G to be connected at the beginning, and I know that A and B are uncomplete to each other, I can get a minimal non-empty get set S separating A and B in G. Okay, and because of minimality, I know that every vertex V in S is going to have a neighbor in A or in B. And so from the previous observation, I know that every such vertex is going to be complete to A or complete to B. Okay? Right. So this partition adds into 2 parts. One is complete to A and the other is complete to B. Let me say these are SA and SB. So if I started with the assumption that both A and B have linear chromatic number in terms of G, then what I can do is that, so either I can find actually a complete pair of linear chromatic number, I mean come from S, maybe ASA or BSB. And if that doesn't happen, then I can conclude that both SA and SB have low chromatic number. And so what this means is S is going to have low chromatic number. Okay. Right, and I can review the second outcome about this linear complete pair outcome to be a good outcome to build a chromatic dense inducer graphs. So for a moment, let me just forget about it and focus on the first outcome, which is a low chromatic cassette. Okay. So what this is going to imply is that, of course, I mean, because I have the complete freedom to choose A and B at the beginning, as long as they have large chromatic number, I can assume that A and B are actually the two components of G minus S with the highest chromatic number, right? They're still incomplete, they still have high chromatic number. And what this means is actually A has to be large. A must occupy almost all of the chromatic number of the host graph G based on the axioms. Okay. So A still have huge chromatic number. And what I want to do next is to repeat this sort of argument inside A. And of course, up to this point means things are going to be more and more technical, and you need more P5 free argument, so more induced P5 free chases. And so I'm not going to talk much about it. But the goal here is that by repeating this sort of thing inside GA, I can hope to do one of the two things. So either I can grow, the linear, the high chi and the complete pairs indefinitely, so that so not just A, I can also force B to have chromatic number, almost all of chi G. And if I can grow indefinitely, and at some point they can get too large, and I can apply the previous observation about P5 free again to get a vertex complete to a huge chunk of chromatic number. And this is going to be a good outcome. And if this sort of growing business cannot be done, then I can actually capture a chromatic dense inducer graphs with polynomial factors, polynomial variables. I'm not going to talk about this. Yeah, but basically, the point of this step is to isolate the original problem into essentially one case of chromatic dense inducer graphs. So basically, so far, what we've been doing is to make the conceptual idea of chromatic dense inducer graphs work. Okay. Yeah, so unfortunately, what I've told you so far is just basically the simpler parts of the proof. The most technical one is actually how we deal with these chromatically dense inducer graphs. And this is done by what is called chromatic density increment. So there is a third idea, which is perhaps the most technical one. And the idea here is that as long as I have an epsilon chi dense induced subgraph, I would like to find inside that another chi dense induced subgraph, but now with density parameter epsilon to the a. So basically, you raise the the density parameter by some large power with a polynomial trade-off on the shrinkage factor in the chromatic number. And I want to say that if this cannot be done, then some other nice things have to happen. But of course, I mean, these nice things can be technical. So, and if you know a bit about what happened behind recent progress on Erdős Hajnal, then this is actually modeled after what is known as iterative specification for P5 graphs. For Erdős Hajnal for P5, but the real thing, I mean, the devil is always in the detail. So the detail, I mean, differs significantly. So anyway, and this is actually where the result Erdős Hajnal for P5 comes in as a black box, because in order to make it work, I gotta use Erdős Hajnal with more structural arguments for P5. And the main reason here is just because for Erdős Hajnal for P5, the specification business works because I could count vertices. But now chromatic number is not working well with counting vertices. So basically, double counting or random sampling or anything similar would not work very well. So basically, all the arguments had to be modified significantly. In particular, this Erdős Hajnal result for P5 must be included, or at least it should be included as an input. Right, so that's the talk, and thank you very much for your attention.
Thank you. Any questions?
So why the chromatic, the increment argument finishes developed?
Yeah, so there's one that I try to hide because it is a technical part. So basically, the final end of the product is that you can produce either a sequence of sets that okay, so let me say a complete multipartite subgraph such that each part is high chromatic or something similar, but not complete anymore. Some sort of chromatic dense similar to chromatic dense graphs, but then that's good enough to extract a big clique, something like that. Yeah.
Thanks.
So I got a little lost. Where were you using everything here is for measures, and you're just saying the number or?
Yeah. So what I'm trying to say here is that all of these arguments works
It's
well.
just for measures.
Yeah. If you replace chi by any measure.
Okay.
Is it essential when you apply induction? Do you have to actually use the measure? Like you couldn't do.
There is no induction.
No induction, but you must have some reason why you use measures, right? Like,
What I wanted
it's a
to
chromatic function.
Yeah, what I wanted to emphasize here is that there is nothing about the clique number. There's nothing about induction on clique number. So normally in chi-boundedness, what you like to do is that you start with a graph with bounded clique number, and then you want to show that it has bounded chromatic number.
Right.
But here it is the other way around. You start with a graph with huge chromatic number, and then you try to deduce properties of its induced subgraphs in terms of chromatic number, in terms of chromatic distribution. And then finally, you get some sort of nice structures. And then you keep iterating that to get a large clique. So what this means here is that a clique of polynomial size must appear in a graph of large chromatic number. Yeah.
So I have two questions. The first one is, by using the technique, can you also show that excluding the disjoint union or P5s also results in a polynomial Hajnal class?
The same technique? You mean the same, exactly this technique?
Yeah, possibly by kind of developing this technique, maybe. Because there are lots of results about the disjoint union and preserving polynomial Hajnalness.
Yeah, so 2 points. First is that I think Gyárfás is still open for disjoint unions.
Yes, right.
Yeah. The second thing is that yes, it is true that from this result you can deduce that this joint union of P5 also satisfies polycapacitance, but it's not going to be using this argument.
Okay.
It is going to be about another argument in my thesis.
I see.
Oh.
So then can it be extended as like so?
Or maybe also in another paper of Merchanovsky and Posimo and Alex Scott and Supispeco. I mean,
I see.
so basically there are two arguments showing that you can
Okay.
actually do it.
I see.
Yeah.
And another question is so fractional product number is also an example of the measure, right?
Yeah.
So my question is there something no result about the fractional version of Gyárfás-domness?
Yeah, so if you don't ask for polynomial bounds, then yes. If you ask for polynomial bounds, then I don't know. So so actually, this P5 thing was first done for fractional chromatic number.
Oh, I see.
So I managed to do that, and then I tried to extend the idea. But of course, fractional is still sort of amenable to counting.
Right.
Yeah.
Okay, thank you.
So did you also use the regularity lemma as like readily?
No. Yeah, I mean that's actually a pretty sad thing because chromatic number is very hard to handle, very hard to break down. Yes.
If you assume some like Erdős Hajnal is true for P6, then can you
Yeah.
deduce?
Yeah. So it's actually
Um,
kind of funny, right? Because it seems like before this work, maybe no one really thought about bootstrapping Erdős Hajnal into polynomially of EK. But after this was done, and I was giving talks at a couple of places, I kept getting this kind of question. So people ask me if is there any chance that I can bootstrap Erdős Hajnal into polynomially by excluding PK? And the answer for now is not yet. And the reason is very simple. So it seems like, in all of induced subgraphs business, high-boundedness, Erdős Hajnal and things involving induced path, the only tool we have so far is some sort of variant of the Gyárfás path argument. And as I said, if you want to move from Erdős Hajnal already to this thing, to this off-diagonal form, you only have to use the fact that you're excluding a path, which means that you have to invent some sort of tool for excluding path. Maybe still a variant of Gyárfás path argument. I have not been able to do that, or maybe some entirely new argument. Already for P6, this seems non-trivial.
What about a different variation of P6, P5, where maybe you add a
So
vertex to
you can basically do this configuration.
something like a broom?
Yeah, a broom. So but it is just sort of traditional kind-boundedness. So whenever you have a path, you can do a broom, I think. But, so you can modify the proof technically to do it.
With poly.
Yeah. Of course, now you have to include the clique number because you are doing brooms. But it's just like technical addition.
What kind of bound do you get? The polynomial bound?
Yeah, what is the degree?
Okay, let me be conservative.
Oh.
No, it is not. Okay, so as far as you know, there's some sort of belief that is almost some sort of C times omega G square, actually quadratic. I think this was conjectured by some people, but I forgot the name. Just that, of course, this method cannot get anywhere close to this. And one of the reasons is because of Erdős Hajnal. So Erdős Hajnal is not even known if you can do Erdős Hajnal optimally. Maybe there's a way to do this, but I don't know.
Is there any lower bound, like some example?
Yeah. So the lower bound comes from Ramsey numbers. So it's basically divided by. There are examples showing that KFG is going to be at least maybe log omega G. And to do this, you take the complement of optimal Ramsey graphs with no triangle. So complement means you have no three-vertex stable set.
You tried to I mean, this is on a different tangent. The question is on a different tangent. So you try to motivate P5 tree graphs by giving examples of some, for example, the clique ring problem. Do you know of any algorithmic implications of this result?
Yeah, so I also get asked, and only until recently that I know. I mean, maybe just on sort of made up. So for graphs problems, I mean, we have three basic problems. I mean, the clique problem, the independent set problem, and the coloring problem. So independent set for P5 tree graphs was solved 10 years ago, or maybe something like that. We can do it in poly time. And for clique, you know that you cannot even approximate it within a factor, something like n to the 1/4. So approximating by this factor is not possible, unless you know unless some highly non-standard assumption is true. Anyway, yeah. So the thing that comes from this work, I mean, hopefully I will be able to update the archive soon, is that you can actually output a clique. So for any input graph G with no induced P5, you can output a clique of size at least something like this, or some C positive. And so basically, I mean, this bits with the general bound, I mean the general inapproximability bound, and also you're also somewhat guaranteed by this inapproximability result for P5 tree graphs. That for cliques you cannot approximate by this factor, but you can approximate. You can output a clique of this size. And the reason here is because this argument is fully algorithmic, modulo Erdős Hajnal. I mean, but you can de-randomize Erdős Hajnal a little bit. And this argument works for fractional chromatic number. And you can approximate or even compute fractional chromatic number explicitly because you know maximum weight independent set for P5 tree graphs. So basically you use maximum weight independent set to solve this sort of clique problem, or at least approximate the clique. I mean, as long as you know about the proof, I mean, about the steps and so on and so forth, then.
So you can't use the independent set algorithm as a black box?
Yeah, as a black box. Yeah.
Okay, as a black box.
Yeah.
Right, any other questions? Okay, if not, let's thank the speaker.